classmates, I'm Alisokin and I'm going to report about the flow in closed conduits, especially in series and parallel connection. So first, flow in closed conduit. Defined as the transport of water in closed conduits that are flowing full. Flow occurs because there is a longitudinal pressure difference along the conduit. Flow in closed conduits pipe if conduit is circular in section and duct otherwise. Differs from that of open channel flow and the mechanism that derives the flow. So in open channel flow, the fluid moves due to gravity, while in pipe, it is more of a pressure difference to make the fluid flow. So types of flow. There are two types of flow. The first one is laminar flow, characterized by fluid particles flowing smoothly paths in layers, which each layer moving smoothly past the adjacent layers with little or no mixing. In laminar flow, the motion of the particles of the fluid is very orderly, with particles close to a solid surface moving in straight lines parallel to that surface. So in laminar flow, for short, it has a smooth flow. So the next is turbulent flow, type of flow in which the fluid particles move in a zigzag way. The eddies formation takes place, which is responsible for high energy loss. Turbulent flow occurs mainly when the liquid is moving rapidly and they are also getting mixed between the layers. The speed of the fluid at that point is continuously undergoing changes in both magnitude and direction. So turbulent flow, from its name turbulent, the particles move not in a orderly way. So this forms eddies, which means the mixing, or it's like regions where the fluid mix. So relationship between velocity and time that cause turbulent flow and laminar flow. This is a graph between velocity and time to see how this flow behaves due to velocity with respect to time. So as you can see, laminar has a straight line because it has a constant velocity, while in turbulent flow, it has a difference in velocity. So the difference in velocity with respect to time, that is the fluctuating component. So that means the larger the fluctuating component, the more turbulent flow. So Reynolds number. A criterion of whether fluid, liquid, or gas flow is absolutely steady, streamlined, or laminar, or on the average steady with small unsteady fluctuations, which means turbulent. So Re is equal to rho VU over mu. Rho, where rho means fluid density, V as velocity, L as length, mu is the dynamic viscosity. Reynolds number is denoted by Re. If the Reynolds number is less than 2000, the flow is called laminar flow. If Reynolds number is more than 4000, the flow is called turbulent. If the Reynolds number lies between 2000 to 4000, the flow may be laminar or turbulent. So next one is head loss in pipe flow. Major head loss associated with frictional energy loss per length of pipe depends on the flow velocity, pipe length, pipe diameter, and the friction based on the roughness of the pipe and whether the flow is laminar or turbulent. Although the head loss represents a loss of energy, it does not represent a loss of total energy of the fluid. The total energy of the fluid conserves as a consequence of the law of conservation of energy. In reality, the head loss due to friction results in an equivalent increase in the internal energy of the fluid. Major head loss in pipe is caused by friction. So if you see a pipe, inside diameter of a pipe, it's not smooth, so that can cause friction. So next one is minor head loss. In an industry, any pipe system contains different technological elements as vents, fittings, valves, or heated channels. These additional components add to the overall head loss of the system. Such losses are generally termed minor losses, although they often account for a major portion of the head loss for relatively short pipe systems with a relatively large number of vents and fittings. Minor losses can easily exceed major losses, especially with a partially closed valve that can cause a greater pressure loss than a long pipe. In fact, when a valve is closed or nearly closed, the minor loss is infinite. The minor losses are commonly measured experimentally. The data, especially for valves, are somewhat dependent upon the particular manufacturer's design. So, in short, minor head loss are the frictions happen in the pipe fittings. So, but in my report, I'm more on the major head loss. So, next is the Darcy-Weisbach equation. In fluid dynamics, a Darcy-Weisbach equation is a phenomenological equation which relates the major head loss or pressure loss due to fluid friction along a given length of pipe, the average velocity. This equation is valid for fully developed, steady, incompressible single-phase flow. So, Darcy-Weisbach equation.
So, the formula is H sub F equals by 0.0826 FLQ squared D over D raised to 5, where F is the friction factor, L is the length of pipe, D as pipe diameter, V average velocity, Q as discharge. So,
these are the some materials used and its equivalent absolute roughness F. So, next one is Manning's formula. An empirical formula estimating the average velocity of a liquid flowing in a conduit that does not completely enclose the liquid. Open flow. However, this equation is also used for calculation of flow variables in case of flow in partially full conduits. They also possess a free surface like that of open flow. So, HF equals 10.29 n raised to 2 LQ squared over D raised to 16 over 3, where n is the roughness coefficient. So, there is also a table for the roughness coefficient. So, next is the Reason-Williams formula, an empirical relationship which relates the flow of water in a pipe with the physical properties of the pipe and the pressure drop caused by friction. It is used in the design of water pipe systems such as fire sprinkler systems, water supply networks, and irrigation systems. It is named after Allen Hazen and Gardner Stewart Williams. The Reason-Williams equation has the advantage that the coefficient C is not a function of the Reynolds number, but it has the disadvantage that it is only valid for water. Also, it does not account for the temperature or viscosity of the water, and there is only valid at room temperature and conventional velocities. So, the formula of Hazen-Williams is HF equals to 10.64 L Q raised to 1.85 over C raised to 1.85 D raised to 4.87, where C is the Hazen-Williams coefficient. So, there is also a table for that. These three formulas, the Manning's formula, the Darcy-Weisbach formula, and the Hazen-Williams formula are used to compute friction inside the pipe, head loss due to friction inside the pipe. So, next are the pipe connections. The first connection is pipes connected in series. When pipes of different lengths and different diameters are connected end-to-end to form a pipeline, such arrangement or connection of pipes will be considered as pipe in series. So, as you can see in the figure, the head loss is the total head loss or the sum of the head loss in each pipe, and the discharge denoted by Q is equal in each pipe. So, next connection is pipes connected in parallel. Are said to be in parallel when they are so connected the flow from pipe branches or divides into two or more separate pipes and then reunite into a single pipe. So, the total discharge is the sum of discharge in each pipe, and the total head loss is equal throughout the system. So, example 1. The system of pipe connection is as follows. Assuming C is equal to 120 for all pipes and assume that the the rate of flow is 0.0085 cubic meters per seconds. Length of pipe A is 2,750 meters. Diameter of pipe A is 400 millimeter. Length of pipe B is 1,830 meter. Diameter of pipe B is 300 mm. Length of pipe C is 1,830 and the diameter of pipe C is 350. Calculate the total head loss of the system. So first, you need to figure if what connection it has. So the pipe A, B, and C are connected from end to end. So therefore it is series. So first, you need to compute the head loss due to friction. So C is the given, or the Riemann-Williams coefficient. So we're gonna use the Riemann-Williams formula. Computing the head loss due to friction is equal to 10.64 L Q raised to 1.85 over C raised to 1.85 D raised to 4.87. So substituting all the given for pipe A, we come up 3.77 meters. So for pipe B, substituting everything, we come up 10.204 meters. So for pipe C, substituting on the formula, come up an answer of 4.816 meters. So the total head loss is 3.77 plus 10.204 plus 4.816. Head loss is equal to 18.797 meters. So example 2, pipe 1, length is 600 meters, diameter is 450 millimeter. In pipe 2, length is 800 meter, diameter is 400 millimeter. Pipe 3 has a length of 700 meter and its diameter is 500 millimeter. There is a given discharge, a total discharge. Q is equal to 0.86 cubic meters per second, which has a friction factor F 0.02 for all pipes. From the system show, compute the discharge of pipe lines 1, 2, and 3. As you can see, the connection is in parallel because there's an inlet and connection of 3 pipes and it joins again on the other side. So on the formula, the discharge is the sum of all discharge in each pipe. So we can have an equation of 0.86 equals Q1, Q2, Q plus Q3. So we all know that head loss is equal in each pipe. So HF1 is equal to HF2 and as well as HF3. So first, F is given, so we're gonna use the Darcy-Weisbach formula. So everything need to be in terms of discharge because of our equation 1. So first, we substitute everything. 0.0826 multiplied by 0.02, which is the friction factor. The length of pipe 1, 600, Q squared over 0.45 raised to 5, which come up to an answer of 53.715 Q1 raised to 2. So for HF2, substitute everything for pipe 2, come up in an answer of 129.063 Q2 raised to 2. So as well as HF3, substitute everything and we can come up answer a value of 37.005 Q3 raised to 2. So we all know HF head loss due to friction or head loss is equal in the entire system. So it is safe to say that HF1 is equal to HF2 or head loss 1 is equal to head loss 2. So Substitute 53.715 Q1 raised to 2 is equal to 129.6063 Q2 raised to 2. In terms of Q1, we can have 0.0645 Q1, or we can say this the equation 2. So, head loss 3 is equal to head loss 1. So, again, in terms of Q1 again, Q3 is equal to 1.205 Q1. So, substitute everything on our first equation. We have the answer. Q1 is discharge 1 is 0.302 cubic meter per second. Discharge 2 is 0.195 cubic meters per second. And Q3 is equal to 0.364 cubic meters per second. So, that's all my report.